All right, so our last lesson. Some people call this Lagrange. Some people call it Lagrange. It kind of doesn't matter. It's someone's last name, okay? It's the Lagrange form of the error bounds, also known as Taylor series. So we're jumping into the last lesson, which is error today. So here's our formulas for it. They are at the top of your page. What we are doing here is this. The only error we know up until this point is our alternating series error, okay? So our alternating series error said what? Do we remember that?
Next omitted term?
Yes. So our series, our alternating series is the error of that series is less than the value of the next omitted term. That's what we did in our alternating series error. So this is just a different way of doing error. Obviously, alternating series only works for alternating series. Lagrange works for everything. Okay, so we will use that for a lot of things. Essentially, what Lagrange tells us is this. Okay, if we have a Taylor polynomial that's approximating a function, we can see how accurately it represents that function. Okay, so f of x in this little equation here, this is our exact value. F of x is the true function. P sub n of x, that is our approximate value. R sub n, this notation, is our remainder. Are we all okay with that equation? The true value is equal to the approximate value plus the remainder or the error? Yeah. Okay, so we would just say it's off by this much. So an easy way to talk about the remainder is to solve this equation for the remainder. So the next equation you see here is r sub n of x is equal to the exact value minus the approximate value. That kind of makes sense for error, right? Yep. Okay? Now, we are going to use the error formula, absolute value of r sub n of x. Why do you think we use absolute value? Yeah, because it could be in either direction. Sometimes we don't know whether our true value is less than the approximate or our true value is more than the approximate. It doesn't matter whether it's negative or positive. We just care about how far off it is, right? So we're going to use this formula with the absolute values on it. Okay? All right, so here's what we do with this. This is going to look super technical, but all we're going to do is walk through how to figure this out, okay? 4 examples of the same thing. So here's what Taylor's theorem says, also known as Lagrange, okay? If a function f is differentiable, blah, 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 we can write a Taylor polynomial. We already know how to do that. We're familiar with that formula, yeah? Okay, so in a Taylor polynomial, our remainder, also known as error, is given by the following formula. Okay, you have this one on your page. And this is our error formula. What does that little f to the n plus 1 mean? The n plus 1 derivative, right? Of z over n plus 1 factorial, x minus c to the n plus 1. Okay, good question. All right, so big question for us is this. How is this different than alternating series error? Because what did the alternating series say? It said if we kind of approximate it up to this certain point, our error is less than the next what? Omitted term. All right, so our big question is this the same as the next omitted term? Yes. Almost. Almost. Except for, why is there a z? All right, so that is our one thing that is really different about this. So when we apply this, z is another number. We don't know the exact value of z. Okay? So what we try to do instead of finding the exact value of z is we find a maximum value for the n plus 1 derivative. We are not always able to find what this is exactly. The Lagrange whole theorem, Taylor's theorem, is all predicated on finding, okay, if we stop at 4 terms, if we can just find the maximum value of the next derivative, the 5th derivative in that case, we would be able to say our error must be less than or equal to that. Okay, so it gives us kind of a range of that. So here is our big formula that you will have to know. Now, we're going to do it enough times that it's probably going to just come to you. All right. This is the part that looks crazy, okay? But let's walk through what this says. The absolute value of f of x minus p sub n of x. What really is that? True value minus approximate value is equal to the remainder. Now, you don't have to write that absolute value of f of x minus p sub n of x, but you should know what that's saying in case it's presented to you. That gives me the remainder. We already talked about that. And the remainder formula is the n plus 1 derivative over n plus 1 factorial times x minus c to the n plus 1. Really, if you know the formula for the Taylor polynomials, like that formula comes very much as part of that, right? We just went up to the nth term, but isn't that just going one more, right? And that's absolutely valued, okay? This is one of those things on a free response that you are going to want to write down that formula first, okay? Because here's the thing, the grading on this, and this I just literally got from listening to her teach this 2 years ago, okay? The grading on this is such that if you don't write that down, but make a mistake in plugging in the numbers, you basically get nothing. If you write it down and then make a mistake, you at least get a point for knowing what you're talking about, okay? We don't want to lose all the points for not, because then they don't know, do you not know the formula? Do you just not know what you're talking about, or did you just make a mistake? They have no idea. So if you know the formula, there's a lot of error carried forward. If you don't write down the formula, there's not a lot of error carried forward, and we don't want that, okay? Know the formula, write it down, okay? Makes sense? As much as we don't want to, I'm going to try to be honest about it. Yes, sir?
And write it down means write all of it down?
That circled part. Every time. Circle part.
Circle.
Small.
You don't have to write the absolute value of f of x minus p sub n of x. It's been really hard for me to get the subs and the to thes and if I'm saying those things right. I really feel like that's where I'm missing line. All right, so note. This is similar to error from alternating series in that you looked at the next omitted term. However, the big difference is that Lagrange forces you to consider the maximum value of the next derivative. That's really the only piece of this that is very different than the alternating series. Really, that's it. Okay? Now, within this lesson, there is some built-in practice over other things that we have been doing so that we can get the feel of free response where you find part 1, find the Maclaurin series, part 2, find this, and so on. So just know that we're kind of reviewing stuff as we go throughout this lesson too. All right, we ready to try this? We're going to get this under control, and we're going to feel fine about it. All right, so in example 1, let f be a function with 5 derivatives on the interval 2 to 3. Assume that, oh look, let's look at this notation. That little f to the 5th of x, what is that? The 5th derivative of f of x. The absolute value of that is less than 0.2. All right, so pause right at this moment. We know that means the 5th derivative is less than 0.2. What is that telling me in terms of what we just talked about with Lagrange? That is the maximum value of the 5th derivative. So look, they're giving me in the problem the max value of the 5th derivative. If you can find that, that's huge. Okay, so that is our max value of our 5th derivative. And we would like the 4th degree Taylor polynomial for f at c equals 2 is used to estimate f of 3. All right, do we remember how to find a 4th degree Taylor polynomial?
Do 4?
You
do 4, right?
Yeah, we need to do 4 derivatives, yeah? All right, so we don't actually have to write the 4th degree Taylor polynomial, do we?
No.
They haven't asked that. So we would just like to know first, how accurate is this approximation? What is that question asking us?
Remainder?
Find the remainder. Yeah, find me the error. How accurate is it? All right, so first thing we write down is what?
The formula?
The formula. All right, we write down absolute value of r sub n of x is equal to, and you don't even have to plug any numbers into this. Just write it down to start with. The n plus 1 derivative at z over n plus 1 factorial times x minus c to the n plus 1. My very next thing I would do is plug in the actual numbers, okay? Now watch how we label this. We have a 4th degree Taylor polynomial. So check out the notation on that formula. On the left, it's r sub what? N. On the right, everything is n plus 1. So when we are writing this down, your r sub is always going to be one less number than everything on the right. So what you are writing down then is this. R sub 4, because it's the 4th degree Taylor polynomial. So this is the remainder after 4 terms. Okay, so your error is going to be the remainder after 4 terms is equal to, but on the right, what derivative are we going to look at? The 5th derivative over 5 factorial times x minus, what are we centered at? 2 to the 5th. So the first thing we do is just plug in things. Now, why do I have a 3 plugged in there?
Because it says x equals 3.
It says we would like to use this to estimate f of 3. That means my x value is 3. And in fact, I really could have done r sub 4 of 3, right? Are we all okay with our formula on that?
So is this the formula we have to know then?
I'd write down both.
What's the difference?
Oh, nothing. That is the formula, isn't it?
Yeah, it's different.
It's
like,
Oh.
it's different.
No, it says m equals.
It says m
Oh,
minus
yeah,
c.
no, I would just know this one.
Yeah.
So you lied to me.
Maybe
Oh, I'm
for
sorry.
next year.
I know. I will change those notes.
I'm just gonna make
Yep,
it.
f of 3 means x equals 3. All right, so the main thing we have to do to figure this out, because we can figure 5 factorial, we can figure 3 minus 2 to the 5th. The main thing we have to do is know how to find the maximum value of the 5th derivative, because that's what f to the 5th of z is. What did we say the max value of that was?
3. No.
0.2. So on the next part, when we simplify, we put that 0.2 over 120. Where'd we get 120 from?
5 factorial.
Yeah, the 5 factorial.
Wait, sorry.
Mhm.
Where did you get those two numbers?
So the maximum value of the 5th derivative was given to us in the problem. The f to the 5th of x. So the 0.2 comes from above.
Okay.
120 is just 5 factorial.
So do we always just use the max value if they tell us?
Yes,
Okay.
always use the max value.
But it's f to the 5th of c. Is that?
That is, that.
Okay.
This is giving us the max value.
Okay.
So we plug that in here. We plug this in here. This gives me just what? 1, right? So at the most, that value is 0.2 over 120, less than or equal to. It does say give this to 4 decimal places, so to save time, because I believe you all can type things into your calculator, our error will be less than 0.00166.
I thought it was just 4.
It is. Rule of thumb is always go 1 more than whatever they say. Remember, if it says 3, go to 4. Every time. If it says 4, go to 5. Type in 0.2 divided by 120 in your calculator.
See, you were wrong. We don't know how to do it.
Basically. Honestly, on the AP test, my rule of thumb is if it says 3, go to 4. If it says 4, go to 5. Always do 1 more than they say. Because then you'll not be rounding off and do something stupidly wrong. Okay? It's just better.
What if they're angry and
They will not be.
okay?
They will not be.
That's not
What if they're cranky?
I have discussed that at length because there are some that say like round to the nearest whole number. Don't round to the nearest whole number. Give it to 4 decimal places. Every time. It's more accurate. It doesn't even matter. That is one place where they don't care like and think that you didn't read the question.
Wait, so if this is round to the nearest whole number, you can round to the nearest.
You can, but if you do it wrong, you're wrong. If you go to 4 decimal places, you're right. So, I don't know. I'd rather be right. Safe. Rather safe than sorry. All right. Part B. Suppose that P sub 4 of 3 equals 1.763. What is that?
The approximate.
That's the approximate value using our 4th degree Taylor polynomial at 3. Use your answer in A to find the interval in which f of 3 must lie. Do you remember when we did the alternating series error, we said the true sum falls between what? Yes, the subtraction thing. You take the approximation minus your error on one side, you take the approximation plus your error on the other side. Okay? So f of 3, the true answer for f of 3 must lie between these two numbers.
We need interpolation.
No, you just need to plug in numbers. So f of 3 must lie between the estimate minus the error
Oh, you do.
and the estimate plus the error. You'd be 100% okay to leave answers here, but this is a calculator section, so maybe not. You know, just go ahead and find your answers.
So, is we like a
Huh?
Eric forward type situation?
This would be.
Like
Yep.
say you're running out of time and you
Mhm.
just make up a value for R sub 4.
As long as it does not overly simplify your answers in part A. Like if you just make it be 3,
Yeah.
that's not going to be,
It's just
that's not going to work for something like that. Overly simplifying is always going to take points off. But yes, if you got R sub 4 of X wrong in part A, you could still get your part B. Yes. Any issues or questions so far?
I don't think so.
Now, all we're doing is practicing this multiple times. There are different ways to present the maximum value of that next derivative. So we're going to hit a couple examples looking at how you might see that. No. Sometimes you have to find it. The next two examples, we're going to find it. Okay? All right. Let's look at example 2. Now, like I said, some of this is helping us review some other things. So part A, if we read it, find the 5th degree Maclaurin polynomial p sub 5 of x for f of x equals sine x. Where should we remember this from?
Like 3 lessons ago.
Couple lessons ago, we talked about sine x, e to the x, and cosine x. These are the ones that we said you must know. So what do we know about sine x? Is it the even or odd one? Do we remember? It's the odd one. So it uses all the odd terms when we're doing that. So it starts with what? X, and then it has minus x to the third over 3 factorial. All right, so we want the 5th degree, so we really only have to go out to what? That's not 5 terms, that's the 5th degree. So we go out to the x to the 5th term, right? So we have those 3 terms. Any issues with that? Now, part 2, not part B yet. Then use your polynomial to approximate sine of 1.45. What does this mean for me to do?
Plug it in.
Plug it in to my approximation. Okay, do you all think you could do that in your calculator?
Yeah.
Okay, great. Here's our approximation. 0.9953. I believe that you can do that.
Or you use sines in one.
No, not sine. You plug that in for x's in your p sub 5 of x. This is our approximation. All right. Then use Taylor's theorem, okay, another name for Lagrange, however you want to say it, to find the maximum error for your approximation. Okay, so let's practice writing our formula down. It would be r sub 5 first of x. And then on the right side, we would use what?
N plus 1 of z.
F to the 6th. Now you can go straight to numbers with that. That's still showing you know the formula. So you can go r sub 5 of x, and you can go the 6th derivative of f of x over 6 factorial. Why is it just x to the 6th?
Maclaurin.
In Maclaurin, where are we centered? 0. All right. So that also counts as writing your formula down. Because we haven't actually plugged, like, other than the n's, we haven't plugged in numbers to this yet, right? That's enough to do. Now, let's talk about that maximum 6th derivative. Have they given that to me anywhere?
No, you
No. You got to figure it out. Okay, so f of x is sine x. Let's think about sine x.
1.
So sine x, the derivative is cosine, and then negative sine, and then negative cosine, and that's how your derivatives would go, yes? Well, let's think about your sine and your cosine function. What do they look like? The waves. Both of those, sine or cosine, have a maximum value of 1. Neither one gets larger than 1, so it kind of doesn't matter which derivative we're looking at. The maximum would be 1. So now I go plug into the right-hand side. The maximum value of the sixth derivative can only be 1. Because a sine and a cosine function cannot get any larger than 1. 720 comes from our sixth factorial. And then we're approximating sine at 1.45. So we go ahead and plug that in for our x. From here, this becomes purely plug it in your calculator. 1 over 720 times 1.45 to the sixth power. Again, calculations give me 0.0129. Our error is less than that number, less than or equal to. All right, now based off of what we did in example 1, do you think you could do part B? Use your answer to find an interval from A to B such that sine of 1.45 falls between them. What's that really asking me to do? Take your approximation minus your error and your approximation plus. Yeah, you use like your radius almost as your like error-ish. Okay.
So 0.9953 minus.
0.9953 minus and 0.9953 plus error. Yes? Now again, you could just set that up and write on the left 0.9953 plus 0.0129 or minus and 0.9953 plus 0.0129 on the right. Or we could go directly to our answers, which I know we don't want to type in our calculators. I'll give them to you right now. Issues, questions, concerns? We okay so far? Look, this is like a full free response. Yay. All right, so part C. Could sine of 1.45 equal 0.977?
No.
No, why not?
It's not in the interval.
Not in my interval.
It's extent. It's not supposed to be.
0.977 is not within my interval, so no. Okay. Give me a minute to write that. Now, you would not see like a part D, probably, but we're going to lead to part E with it. What is the actual value of sine of 1.45? What would we do? Plug it into our calculator. What mode? Radian. Okay, so there's my actual value. But this is really just leading us to part E. They probably would never ask part D. They would probably just jump straight to E and expect you to understand this notation. How big is your actual error? F of 1.45 minus P sub 5 of 1.45. What is this asking me to do? Take the true value minus the estimate. But what's the absolute value do?
Makes it positive.
Makes it always positive, right? So if I did that, I would get about 0.0026. And this is another reason why on those other questions, when it says go to 4 decimal places, why it's good to go more than that. Because if everything is supposed to be accurate to 4, and I'm rounding everything to 4 on the way, is my next answer going to be accurate to 4 necessarily? Maybe not. Okay, so maybe it's worth going one more. All right, so is this bigger or smaller than our maximum error found in A? This is smaller. So our error is less than or equal to the maximum error we found in part A. Issues, questions, problems?
Oh.
All right.
Excited guy.
We ready for another example where we have to find it? Gavin, am I waiting on something? Oh, Gavin, I'm so disappointed that my video didn't actually record audio because in the middle of it, my husband came in. I said, oh, we're recording for Gavin. You want to say hi? And he goes, no, and sits down. Darn it, you could have heard that. But no, silence instead. Ah, I was enjoying that. All right, here we go. I know, Mima's very mean.
Yeah, she is.
All right. Let's go to the example 3. We have that one and then one more. And then we're going to practice with a free response if we have time still. Okay? Because we need to. All right. Here's another time we get to show what we know. Write the 4th degree Maclaurin polynomial for f of x equals e to the x. Do we remember that one?
I don't remember anything.
Okay, sine was the odd one. Cosine was the even one. What was e to the x? All of them. And they were not alternating. So how does it start? 1 plus x squared plus. Okay. Now this one says 4th degree. So we go to 4 degrees. Yes.
Ours says Taylor on our notes.
Oh, does it? Magical. It should say Maclaurin on that one because Taylor would have to tell you what it's centered on, and that one doesn't say it. It should say Maclaurin here. All right. So we write p sub 4 of x. Now, quick question. It says 4th degree, so we go out to four terms, yeah? Or, excuse me,
Factors.
the 4th
And
degree. I'm losing my mind. All right, we go to that. Do we write plus dot 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 on this one?
no.
Okay, so quick reminder. If it says Taylor series or Maclaurin series, we go dot 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 out to the general term summation. If it says polynomial,
No.
we just go to whatever degree they say. No dot dot dots. All right. Any issues with that part? Okay. Now, we would like to use our polynomial to approximate just e. Okay, that's e to what power? Focus. Sit down. No one cares about the people running on the track. This is e to the first, so what x value are we using? 1. This is telling me x equals 1. If it said approximate e squared, x would equal 2. If it said approximate e cubed, x equals 3. In this case, it's just x equals 1. So how do we do that? Plug in 1 into our calculator. Again, we'll just trust me to do the calculations on this one, okay?
1 plus 1 plus 1.
All right. That gives me approximately 2.7083.
What'd you say about the polynomial?
Polynomial means you cut that off at whatever term it tells you to. In this one, it said the 4th degree, so I cut it off at 4th degree. If it says series, that's where we write the plus dot 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 plus summations.
And then we
Yep.
get the actual, right?
All right. Now, this just says find a Lagrange error bound for the maximum error when x, absolute value of x, is less than or equal to 1. All right, so how do we start off? Write the formula. So it's going to be r sub what? 4. And on the right side, everything's going to be 5. All right. So r sub 4, absolute value. Our remainder is less than or equal to. On the right side, what does my formula say? Let's practice. Which derivative?
To the 5th.
5th derivative at z over 5 factorial times x minus
X to the 5th.
just x to the 5th, right? Because it's at
This is Maclaurin.
0. Now, x equaling 1 does not mean c equals 1, right? It's Maclaurin, so it's still centered at 0. We'll worry about the x in a minute, okay? All right, so our formula looks like this. All right, so before we go plug in things, what do we have to find?
See?
Yeah, that is our max value of the 5th derivative. All right, so let's think. The last one we had to think through, sine became cosine and then negative sine and cosine, and what's the max value of that, right? This time, this is e to the x. So what are my derivatives? E to the x infinitely, yes? All right, now here's the issue. What does e to the x look like?
It just goes to infinity.
It goes to infinity, right? Dylan, do you have a question?
No, I was.
Okay, good.
My bad.
All right, so there's an extra little piece of information in here that we haven't used yet. It says for the maximum error when what?
Oh, when it's negative.
Absolute value of x is less than or equal to 1. So this means x can be between -1 and 1, right? That's what the absolute value of x is, less than or equal to 1.
So E, right?
So e, why?
Because
Because
that max it can be 1.
That would be the biggest value of the e to the x function on the interval -1 to 1. So think about it. If I plugged in -1 to the e to the x function, that's going to be 1 over e. If I plug in 0 to the e to the x function, that's e to the 0, that's just 1. And really, if we think about it, our e to the x function is always increasing, right? So essentially, all you're doing on that is saying to yourself, if this is my e to the x function, and we're just looking at the interval -1 to 1, where's the max value going to be? Well, over here, right? Because it just keeps increasing. So my max value of my derivative, my max fifth derivative, would be e. Because it's e to the first. The derivatives are always e to the x, and the biggest place would be at e to the first. We put that over 5 factorial, 120, and we plug in our 1. Are we all cool with the e?
Wait, so we just plug in e to the 1 equals e.
Correct. That decimal, if I type it in my calculator, is 0.0226. And then find our interval such that e falls between these two numbers. What's that asking me to do again?
P4.
Approximation minus our error, approximation plus our error. See how this just keeps coming up? Again and again and again. All right, I'm going to jump straight to the answer on that. E falls between approximation minus 0.0226, gives me this number. Approximation plus 0.0226, gives me that number. Yes?
So how do we know the intervals is from -1 to 9?
Because they say when absolute value of x is less than or equal to 1.
That means 1 is the radius.
Essentially, yes. That means my x must fall between -1 and 1. Those are my only options. Okay. Last example. All right, I know you're also sad to leave. I know. Hey, might be nowhere else, but we're sad to leave this. All right. Oh, look, this is the fun kind where they give me all the information. Okay, we've given us derivatives. F of 2 equals 6, f prime of 2 equals 4, f double prime at 2 equals -7. Do we remember how to write our Taylor polynomials when we're given this information? Yes. Yes. This is write your Taylor, third degree Taylor polynomial for f about x equals 2. So we're centered where?
At 2.
Centered at 2. All right, take a minute. Just write down your Taylor polynomial. Third degree, so we go to x to the third, or x minus 2 to the third. Yes?
Is it P?
P sub 3.
Of 2?
No,
Of X.
because that's our center.
Okay, that's what I thought. I'm just sorry.
First, we write P sub 3 of x. Then we will use P sub 3 to approximate f of 2.3 in a moment. Do you like how we're rolling the practice with writing the Taylor polynomials back into this? Starting to review already. Next class, lots of review. Well, it's good for you, right? Honestly, in a weird way, this one makes me feel better about everything else because I'm like, oh, I do remember things. Great. I don't know if you're feeling that with me. I am.
Okay, so then we plug it.
Or I'm just being optimistic. Not sure. But
We remember nothing.
in some ways, it is oh, I do know things. Yes.
I will never ever claim to.
Oh, lies. Don't do that. All right, so we start with our 6 plus.
What did I do?
I don't know. What did you do?
You never know what you do. You just do it.
Oh, I was wrong as well.
All right, so there's my Taylor polynomial.
That's right.
Do we feel successful at that? Except for Gavin. What are we doing?
I did the.
You're writing the remainder. We're not there yet. Right now, we're just writing the Taylor
I was
polynomial.
excited, right?
I know, you're just getting really excited about the Lagrange error.
Graduate already.
No!
So
You're stuck with me. All right.
so over this.
Next part on that says we would like to use this to approximate f of 2.3. Yes? What does this mean? Plug in 2.34
X.
x. All right, so writing that out. Honestly, if this was a free response, I 100% would not actually show 6 plus 4 times 2.3 minus 2 and all of that nonsense. Okay? I would show this notation and I would type it in my calculator. And I would get this number back out.
Do you have to have the f of 2.3 in front of it? to
You
get points?
should, because it says approximate f of 2.3. So if you've labeled nothing as f of 2.3, are you actually finding it?
They're gonna beat you.
Wait, so what is happening?
This means we are approximating f of 2.3 using our polynomial p sub 3 by plugging it in.
Just makes
I just did it all.
Oh, Wednesday schedules always mess with my stomach.
Gavin, I feel like you're talking over here and then lost. No.
But if you just throw things at him until he listens. Okay.
I know, because this is reviewing old lessons. So that when we have a test in 2 days, 2 class periods, we're not freaking out.
Is the 6.921 just our answer, right?
2 class, huh?
Or on Saturday.
Oh, yeah, there.
Test on Saturday and test on Monday.
Yeah, sorry, where we're at. Oh, dear God. For the record, whoever's listening to this, Gavin just shoved Dylan out of his chair, and he fell into my desk. No one's injured, but Dylan's still sitting on the floor.
Well, I decided.
All right, we're gonna finish this because we're getting off track fast.
No.
All right,
Getting off track.
read part B. The fourth derivative of f satisfies the inequality f to the fourth of x is less than or equal to 9. Have we seen this before? Yes, what is that giving me?
Next, I'm gonna term max value.
That's my max value, okay? So I'm going to start off saying, if I'd like to use the Lagrange error bound, all right, r sub 3 of x is less than or equal to, let's practice writing our formula. What comes next? What derivative of f?
4.
Fourth derivative at z over 4 factorial times x minus 2 to the fourth. Good.
How do you know when to use that? Like, how do you know
It must either say Lagrange error bound, Taylor's theorem, something like that. There was nothing about error.
Wait, what's the?
Remember, f to the fourth of z, that all that is saying, you're never going to know what z is. That is saying, what is the maximum value of the fourth derivative? That's all that says.
Did we
Okay?
get the x minus 2 from the original?
Yes, because it was centered about x minus 2.
Okay.
Yep.
Wait, no, it's 9.
All right, so what's our max error on this one? Or our max fourth derivative, excuse me?
9
9.
over 24.
So we do 9 over 24.
times 0.3.
Yep. Where do we get the 0.3?
You're doing
We're
zero-
plugging in 2.3 minus 2 to the fourth.
It's
All right,
It's
so
gonna be
lovely number. Again,
0.0081, right? Or like
0.003. This says go to 4 decimal places. I don't know why her work doesn't do that. I don't care. Okay, at this point, we've done enough on this.
Okay, now we do the interval.
Yes.
One more.
Yes.
Wait, is it 9 because of the top thing?
Mm-hmm.
One more round.
Are you sure that equals 0.01?
Yes, I'm sure. Could f of 2.3 equal 6.922? How would we know this answer?
Interval.
Do your interval.
Yes, it can.
Okay, last part of that is true value f of 2.3 falls between, what's on the left?
6.918.
6.921 minus 0.003. Okay, and
6.924.
okay. Oh, look, we didn't even answer that in part B. It says find that interval. I just jumped right to C. Now, could that fall there?
Yes.
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 It's in the interval. Slow clap, fast clap. I don't care. Golf clap. No, I'm not golf clapping this. All right, we're done. All right, friends. Good job. I know it's hard.
Oh my god.
Oh, Gavin. Just one more for the video. You want to wind right into it? Oh my god.